All right, let's see how we go then. Evening all. So this evening I'd like to talk to you about some testing that I've done on antennas. I've called it comparative testing because my intention really is to compare a bunch of antennas and find out which is the best one. The sort of testing that I've done here is it's not the sort of testing I suppose that you would get if you went to an external test lab, a proper lab, because everything in that situation will be calibrated, and that's an important difference here. I'm less interested in the absolute measurements of the antennas that I'm looking at. I'm really only interested in which one is better. So with that, let's move on. So the agenda, as you can see on the screen there, I'm going to go into a little bit about why I'm interested in tennis and how I got into it. I'll talk about the style of antennas that I've tested, and in fact you'll see that it is only one style. The installation scenario, so these are the situations in which the antenna is used in the field. The parameters of interest, the test setup. So I've done various different tests, and I'll talk to those tests individually, and how I've set them up, and what I've been thinking about, I suppose, when I do those tests. And included in that, of course, is the equipment needed. I'll talk, and I guess part of this actually is also very much where to test. So I'll discuss that, and then a couple of other bits and pieces as we go. So kicking off then with why I'm interested in antennas. Well, I guess antennas are just interesting anyway. At least I think so. But why here? Why now? For me, it was through work. So I work for a company that makes smart meters, and smart meters, as you may well know, gather data. You've got to get that data back to somewhere so it can be processed. So what you're talking about there is a communication path, and in the smart metering business, that communication path is frequently cellular. Cellular is great for the company that I work for because it's ubiquitous in the markets we operate in. And so part of using cellular, of course, so what we're talking about is a cellular modem, essentially. You know, it's kind of the heart of your phone, I suppose, without the screen and all that sort of stuff. Cellular modem, and obviously to make the modem operate over the cell network, it needs an antenna. And that's how I got into this, really. I was working, so go back approximately 5 years or so. We were using 4G modems and 4G antennas, and then about 5 years ago, we saw a change in the the cellular operators started to roll out a new technology which was known as Cat-M1. So this sort of sits under the umbrella of 4G LTE, and Cat-M1 brings some good stuff, and we were interested in it for our application. But this introduced a problem because the Cat-M1, as it was rolled out in Australia and New Zealand, introduced a new frequency band that we weren't using on 4G, and that frequency band is band 28, and that covers 700 meg to 800 megahertz. And we found that the antennas that we were using up until that point didn't perform particularly well at that lower frequency. They were geared at the 850 plus part of the spectrum. And there's, you know, if you look at the cellulars, the bands, the spectrum that's used by the telcos, there are pockets of frequencies. There's 900 meg, which is a really common one. There's 1800 meg. There's 850. There's a bunch of them, you know. So we were interested for our application in this new band 28, as well as band 3 I've noted here, and a couple of others, you know, which we'll use. So yeah, that's it. That's how I got into it. So this is going back probably 5 years. What I should add then at this point is that everything that I know about antennas, I've learned in that 5 years. It's all self-taught, and I say that because I may well make some errors along the way. So I'd appreciate if you could correct me. This is an audience, obviously, of people who are familiar with antennas, and I would love you to jump in and call out stuff that I'm doing wrong. So the antenna style. I mentioned there was only one type, and it's this. We call it a paddle pop antenna or a blade antenna, as it's sometimes known. I don't like the term blade because that to me um, is the antenna that you use on your cars for the car radio. It's that thing that looks like a shark fin. I tend to think of that as a blade antenna. These are regarded as paddle antennas, paddle pop. They are budget antennas, there's no doubt about that. This particular one on the screen has only half a radome. That's the plastic bit on the left. On the right hand side you can see that's double-sided tape, and so they've saved money here by only having half a radome. The antenna element itself, the radiating part, is PCB, and there's an example at the bottom there of one. It's FR4 PCB. It's all etched on a single side. This particular one is 0.4 millimeters thick. It's RG, the cable now is RG174, terminated with SMA. You can get them, in other cable types and connectors, but it's what we happen to be using. There's a bunch of these out on the market, and they are all incredibly similar in their form factor. This is 115 millimeters long by 20 mil wide, and as I mentioned, 0.4 thick. And yet, gosh, there's a whole bunch of them out there. You can pick up all over at eBay and similar, as well as much more established manufacturers. There's a little fly going around here. So I think that's probably what I need to say about the antenna itself. Just to comment then on the testing that I've done. This is just a global comment to say when you're testing, when I'm testing of anything, make sure it's representative of the field. Antenna testing is frequently done in free space, and that's great for comparing, for providing a common point of comparison. But that's not realistic, of course. So I've gone to some lengths, and you'll see this a bit later. I've gone to some lengths to make sure that the way I've tested are as representative as I can make it of field scenarios. That's not always the case, and you'll see I did some testing in the office, but I'll talk about that. So where is the meter installed? We've got on the pic on. Excuse me. So on the screen here, you're looking at one of the electricity meters by my company. The right-hand image, you can just make out the antenna is shoved behind a bunch of blue cables. So this is a couple of things to note here. The cables are there to make it field representative. That's of course how how a meter would be connected in the field, and I've done this particularly because we know that these antennas are highly influenced by the proximity of metal. So you've got a bunch of cables, a load of copper work there, and so I wanted to make it as close as possible. The antenna it's fitted. Let me go back a step. Sorry. So the photograph on the left is the electricity meter, and that grey square at the bottom is what we call the terminal cover. So the terminal cover covers the electrical cables, and that's where the antenna is frequently installed. Moving on. These are some common installation scenarios here. This is what we see in the field. So just to explain this image here, we've got three different scenarios. The large box is the electrical cabinet, the likes of which you'd find on the side of your house. It's just a metal box with a hinged door, usually. Inside that metal box is the electricity meter, that's the smaller box. And then the coloured bar is the antenna itself. So the photograph we just saw in the last screen is the central one here. So it's the antenna is installed underneath the meter terminal cover. So I've tested there. The antenna to the right is installed on the metering backboard, I think it's called, board. So inside your metering box, there's the back of the box is lined with an insulating material. Sorry, it's not correct to say it's lined. Actually, it's a hinged door or something or whatever. Point being, though, it's a large piece of insulating material, and your antenna gets screwed. Sorry, your electricity meter gets screwed to that insulating panel, as well as anything else that's in the metering cabinet. They'll get screwed to that. So the second scenario we see quite commonly is that the antenna is on that board, and the third one on the left, the antenna is mounted directly onto the metal electricity cabinet. This one is shown on the front door. In practice, they're actually on the side, because if you picture how the door opens, you know, you'd be putting on the cable all the time. So we know that the antennas are adversely affected by metal. So it's really important that you know that my testing sort of went into that a little bit, and I'll talk more to that in future. So clearly, you can see, you know, I've tested in these three scenarios. These are my main, my field scenarios, if you like, that I've tried to replicate. They could be in other. The antennas could be in other places, but they're generally not. And I think mainly the reason is that the electricity box is not owned by the homeowner, and obviously I'm talking about residential there. Whereas if the meter installer tries to stick the antenna on the side of someone's house, for example, and that clearly is the property of the customer, you can see that conversations may ensue. So these are the three most common types. As well as these installation scenarios, then we have different meter types, which I tested, and I guess as an umbrella statement here, there's, I've said, an infinite number of variations that you could see on site. So I need to kind of just select the ones that I think are going to be the most useful and focus on those. Right, so parameters of interest. If you look at an antenna data sheet, you'll see a whole bunch of antennas, a whole bunch of parameters, some of which are more or less useful. The ones that I'm interested in are on the screen here. I've broken them into two categories: those that I can test on the bench and those that I can't test on the bench. So just to run through those, then there's VSWR and impedance. Those are tested with a vector network analyzer. I do them on the bench, and then there's the physical properties of the antenna. Of course, it needs to fit in the space available to it. The parameters I tested in free space then was gain. Essentially, that was the only one I measured in free space. From that, I was able to derive radiation pattern. I could not calculate efficiency, which was a shame really, because I would have loved to have done that. It was a really I consider that quite a useful metric, but because my whole test setup is uncalibrated, I'm only able to make relative measurements, and I didn't want to go to the inconvenience really of calibrating everything. I felt that was overkill, honestly, for this sort of testing. So I tried to keep it simple. Just one more comment then on these. Those that are tested in free space, I tested them in free space because I needed another antenna, as part of the test setup. And you'll see a bit later that I need some space, 3 meters or so between these antennas, and that clearly wasn't going to be possible in the office environment. So that was really the distinction here. That's what determined where I did them. Of course, I should have done really VSWR and impedance in free space. Acknowledging that there will be the environment around the antenna is going to have an impact on those parameters. But I decided not to because, back to the point that I'm only taking relative measurements. So anything, a brick wall or a computer or whatever it is that's around about my antenna and causing influencing my measurements, all those things are consistent from test to test to test and from antenna to antenna. So I just didn't care really, and it was easier for me to test on the bench, of course, than in free space. So what am I interested in? So VSWR, let's talk about that. On the screen here, you're looking at what's a nano VNA. A VNA stands for Vector Network Analyzer. Sorry, I appreciate that you guys know what a VNA is. I used it for VSWR and for impedance. It's a lot easier to test, of course, than gain. Although you could argue that gain is probably the most useful measurement. VSWR just gives me another data point really to look at. So the picture on the screen here, you can see that I've just calibrated the network analyzer. My 50 ohm terminator is fitted on the left port, and I know I've calibrated it because my line there says, because I'm set to VSWR. My line is completely flat. If I look at the markers at the top of the screen, they're all reading VSWR of 1, indicating a perfect match, which is obviously. I love this instrument. If you don't have one, I would recommend you go and buy it for $60 or whatever they are. There's a bunch of them available, covering different bandwidths and different functionality. Because it's an open source thing, a few people have jumped into the development arena of this, picked it up, and there's different versions of hardware, different versions of firmware available for this. Yeah, I love this toy. So how did I do VSWR? I measured it in a number of different scenarios. This one here is all done in the office. I wanted to find out the influence of an electricity meter to the performance of the antenna. So what I'm doing in this test is I'm taking a measurement at a known distance from the meter, and then I'm changing that distance, taking another reading, and so on, all the way, yeah. And I would do that until I saw that the results weren't changing. So my first measurement would be adjacent to the meter, and then I'd move progressively further away, measuring and measuring until I stopped seeing a change in the results. I also did a test that I termed free space. It's really not free space at all, of course. But once again, because I'm interested in relative goodness only of the antennas, I felt it was a bona fide test. Another VSWR test I've done here, I'm looking for the influence of having the cable coiled up. What we see in the field is after the meter is installed at the cable, if there's any excess coax cable, it might just get, I don't know why we're changing screens here. Let's jump back a second. Yeah, we see that any excess coax would probably be bunched up, cable tied, to keep it out of the way, or maybe just shoved in the corner of the cabinet, whatever. Point being, though, that the cable is not laid out nice and straight. So I wanted to test for that. The test here, you can see I've wrapped it around 4 times around the glass. The number 4 is arbitrary, really. It was just determined by the length of the cable. But importantly, every antenna I tested had exactly the same number of turns. The glass was the same distance from the edge of the desk. My body was the same distance away from everything. What I really focus, and I always do this when I'm testing, focus on repeatability. Make sure that everything that's within your control is consistent from test to test. The reason I think, and I'm not entirely sure of why the coiling up of the cable has such an effect. One reason I suspect for this is that the braid on the outside of the cable does not cover 100% of the inner core. Antennas manufacturers publish this braid coverage, and 80 to 90% might be quite common. And I think, again, in order to keep the price down, cheap coax cable would have less metal in it, and that would ultimately mean less coverage. So because it's not perfectly covered, I think you get electromagnetic fields will leak. Enough said. So I tested in this scenario. Oh my. Let's go back. So what you might be wondering then is just how much influence coiling up of that cable actually has. So if you just look at the graph on the right hand side, ignore the left, I've tested the cable in 4 different positions. The dark blue is straight, I've pulled it taut, and then I've wound a tight coil, a loose coil around the glass, and then I put random, which was, I can't remember exactly how that was, but random, but the same from antenna to antenna, just to make that a bit clear. So what you can see from these results, I think, is that a little bit of coiling actually helped this antenna. You can see that the loose coil there, which gave me the best results, provides a VSWR of somewhere between 1 and 1.5, so that's pretty good actually. And this is over the entire band 28, so you can see the markers at the bottom there, 7 to 800 meg. So that's what a coiled coax cable does to your performance. So back on this, the influence of metal. I did a test where the antenna is in close proximity to a metal plate, and then I moved it progressively further, same as I did with the meter. The metal plate, of course, is there to simulate an electrical cabinet. The cabinet is earthed, so although it's not shown in this photo, I did some testing. It is earthed anyway. I made sure that plate was earthed. Whether it actually makes a difference, I'm not sure, but nonetheless. The conclusion from this particular test, and sorry, just to point out here that this table is plotting the VSWR at a single frequency, 710 meg, whereas if I go back to the slide, this graph here covers 700 meg all the way to 800. But for the purpose of to answer the question of just what influence does metal have, I think it's adequate just to take a single frequency. So at 710 meg, you can see that starting at 30 centimeters, there's not much difference between 30 and 20 and all the way to 5 centimeters. But if you get any closer than about 5 centimeters between the antenna and the metal, that's going to affect your antenna performance. So another measurement, another type of measurement, and this is impedance. On the Smith chart is covering the entire range. The Smith chart is covering the range 700 meg to 2.7 gig. That's pretty broad. As I mentioned, not all of those frequencies are used by the cell network, of course. It's just a selection of bands. But you can see that making sense or trying to interpret the Smith chart on the left like that is just doesn't really make much sense. You wouldn't be able to compare this antenna to another one. It just looks like a scribble, really. So what you can do, however, is focus on a little bit closer, and in my case, band 28 was the most interesting one for me. I've said limited usefulness here. I think if I'm not designing antennas. I've got no control over the impedance of that antenna. The only thing that might be useful to me here is if I see a really tight circle just around my 50 ohm, that would be nice. And then if a different antenna had a circle, out towards the outside of the Smith chart, I could draw a conclusion that the one closer to the center was better. But really, I think limited usefulness, and also because, of course, this is just going to be reflected. It's going to be manifested in other tests that I do. Right. Okay, so let's talk about gain then for a moment, and in the same breath radiation pattern. So gain with antennas is that headline figure, of course, and that measure of goodness that you use to compare one to another. the way the gain is measured, of course, is at multiple points around the antenna in a three-dimensional space. And I don't find it a particularly useful figure, and the reason is because the gain varies at each point. And so what an antenna manufacturer would do, of course, is they would pick the biggest number and they would publish that. And the biggest number, i.e. the best gain, is where the red area is on this, and that's perfectly in along the x-axis, y-axis, along the flat. If you take those multiple measurements in a 3D space and you plot them, you end up with the radiation pattern. And the radiation pattern we're looking at here is for an omnidirectional antenna, which is the antenna that I'm testing. Now, although obviously gain is that headline figure, when I did my testing, I didn't measure gain. I flipped it around and I measured sensitivity, which is the other side of that coin, if you like, because antennas work exactly the same transmitting as they do receiving. I can get away with this, that's called reciprocity. And for my testing, it was just easier actually to use my test antenna. Sorry, to use the antenna that I'm testing, to use that as the receiver, and then I had a second antenna which was transmitting to it, and I would simply measure how much signal strength I would receive. Once again, important to note that all my measurements are relative. So this is my test setup for sensitivity. The only piece of equipment, really, the fundamental heart of this is the spectrum analyzer. It's important that the spectrum analyzer has a tracking generator to do this test. So what the tracking generator does is it sends out a signal, it generates a signal, if you like, and that signal is synchronized with the analyzing portion. So just to put that differently, the equipment will transmit a frequency, and simultaneously it will read in the power at that frequency. Each one of those ends is connected to an antenna. So my test setup is really simple. I've got my frequency generator, that tracking generator, going to the antenna. Now, because I found that I needed an amplifier here, just because I couldn't, the output power of this spectrum analyzer is 0 dBm, so that's 1 milliwatt. It's not a great deal of power, and I found that when my antennas were distances apart, I was really struggling to measure the power, and so I had this inserted this amplifier. I'll talk a bit more about why it was difficult a little bit later. But just to recap here, I'm transmitting a signal on the left, and then some distance away is my antenna that I'm interested in, that I'm testing, and that antenna is also connected to the spectrum analyzer, and I'm reading in the power that it receives. So, so we've got three main bits here. There's the receive antenna, the transmit antenna, and the spectrum analyzer. So I'll just talk now about those antennas. The frequency generator, just to make this comment, is outputting a continuous wave. So that's a pure sinusoidal wave. It's not modulated in any way. Okay. So let's talk then for a moment about the transmitting antenna that I use in my test. The first thing, of course, when choosing an antenna is make sure that you've got the frequency range correct, or either that it covers your frequency range of interest. I mentioned in the last slide that I needed a 20 dB antenna in my setup, and the reason is that I had an omnidirectional antenna to transmit with, and of course, by radiating in all directions, I wasn't getting enough of the energy directed towards my test antenna. So I needed a directional antenna, and the one I ended up with was a log periodic. It achieves this directionality, of course, by, well, it's narrowing of the beam width, basically. It's the same thing. The picture on the screen is not the actual antenna I use, but I've got this here just to highlight how it's constructed. And you've got these left and right elements. And if I show you now the antenna that I actually use, which is this one here, it's just less clear. So I thought the previous image was easier to see what's going on. So this is the actual antenna I used, made by a guy called Kent Britton over in the States. And Kent Britton, for many of you who possibly know this name, is a prolific antenna designer. I forget how many he's made, 10,000 antennas or something in his career. And he sells his antennas over the internet. And I bought this one here. This was about $35 US. I bought some others as well, covering different frequency ranges. But yeah, nice antennas, I guess. So let's talk for a moment then about where I did this testing. So I'm looking for an environment that is both noise-free and free space. And so what do I mean by those terms? Well, noise-free, I don't want any external signal coming in that's going to influence my test. And free space, I don't want any objects close to me that are likely to reflect the signal, create peaks and troughs, and yeah, influence my signal. So there's two ways that you do this typically. The first one is the anechoic chamber on the left. So an anechoic chamber does a great job of representing an infinite space with nothing in it. I didn't have access to an anechoic chamber, so I used the poor man's version, which is the open air test site. And just to talk about this particular test site, you can see obviously there are some trees and so on. I've been careful to try and make sure that I'm pointing my transmit antenna into an array of space. I think the tree to the left is possibly a little bit close. It's probably within that beam width and may influence my signal. So I'm just going to probably just duck back then to the previous slide. So beam width here. To the right is the radiation pattern in for different frequencies. That's what the three different lines are. So if we just focus on the red line for a moment, this antenna has a beam width of approximately 30 degrees. So if you go to the 30-degree point, or even the negative 30 degrees, that would be 330. That takes me down to a 3 dB below the peak. That 3 dB point is where the beam width is measured. So here we have a 30-degree antenna, but that's not the full story, of course, because there's quite a lot of signal is radiated wider out than that 30 degrees, which leads me to wonder, I suppose, whether that tree on the left was a bit close. And I think I observed it at the time, but it was the best I could do, I think, because I'm on a public thoroughfare there. I'm in a park, actually. So that's yeah, those are the two environments really. All right, so let's just talk for a moment about the considerations when choosing a site. I've touched on these already, but just to drill down a little bit deeper. First and foremost, the noise floor. So I'm really interested in noise, or perhaps the absence of noise, in that 700 to 800 meg spectrum, because that's where I'm measuring. So I need to know that there's no electromagnetic noise, or it's not possible to say no noise, but the present noise, the noise that's present there, will be significantly below the signal that I'm trying to measure. Because if it's not, then I just won't be able to measure my signal. I won't be able to pick it out. And then the other point, again, I mentioned this already, but reflection, because any if the wave is modified in any way, be that through reflection, through scattering, or refraction or diffraction, I've got here, this is going to lead to one or two things. It's going to lead to plain old attenuation of the signal, which I don't want, or it's going to set up multiple paths for the signal. So I've got the same signal now, traveling in two different directions, two different paths, and quite likely more than two. As the signal hits an object, bounces off, possibly strikes another object, bounces off. This is going on, repeatedly. I've now got this multipath environment, and those waves will provide constructive and deconstructive wave patterns. And so what do I mean by that, constructive and deconstructive? Well, I simply mean that the two waves, the amplitude of the two waves is added. So the image in the right-hand corner shows two grey waves, and you'll see that there are occasions where the peaks of those waves line up perfectly. And you'll notice that when that happens, the blue signal is at its largest. Now, the blue signal is the addition of the two grey. Similarly, of course, when the grey signals are out of phase, so now you've got a maximum of one wave coincides with the minimum of the second wave, add them together and you get close to zero. And that's what's shown in the middle of the blue wave there. So constructive and deconstructive wave patterns. And if I'm unlucky enough that my test equipment is located in a peak for one test and then possibly in a trough for a subsequent test, that's going to give me a real significant difference in what I'm measuring, and I don't want that. I want consistency. Right, so let's talk for a moment then. How did I find my site? Well, there was a time when I would just load up the spectrum analyzer into the car. I'd stick my omnidirectional antenna on the dashboard, and I'd drive around and very carefully, with one eye on the spectrum analyzer, one eye on the road, I would just look for a site where there was no noise, where the spectrum was non-existent, depressed, if you like, at that 700 to 800 meg range. What I'd then do is I'd get out of the car and try and find a suitable spot, where I really could set up the equipment, because it's not sufficient, right, just to have a place with no noise. As I mentioned in the last slide, it also needs to be free of objects. So that's how I used to do it. But what really changed my life was this app. So this app runs on my Android phone. It's called Oz Phone Towers, and the best as I can tell, it maps all of the cell phone towers across Australia, and that's what the coloured balloons represent. And in fact, each colour is a different cellular operator. The other nice thing about this app is that you can filter by frequency, by cell operator, and some other things. So for me, I was filtering by 700 meg. And it was just such a great tool. It meant that I could fairly easily find a location that was close to my home, because I want to minimize my travel time. Close to my home based on the absence of balloons on the map, and then I'd get to site, I'd unpack the equipment and just confirm really that there was no noise. Remembering, of course, that I'm interested, if I'm measuring the 700 to 800 meg range, that is going to come exclusively from cellular towers. I say exclusively. I mean, I'm sure that there are some interferers out there, some interfering noise sources, but generally speaking, it's the cell towers that are my problem. Right, let's talk then about test considerations. Still with that. Before I even set foot on site, I had two real fundamental questions that I needed to answer. The first one was, how far apart do my antennas need to be? And the second was, how high do they need to be off the ground? So just talking about how far apart then for a moment, what I need to achieve here is the measured signal needs to be in the electromagnetic far field. So this is the point, of course, that the electric field the electric wave and the magnetic wave converge, and they form an electromagnetic wave. And that's the way all antenna testing is done. I mean, there is some specialist stuff done in near field, but if you're measuring, if you're interested in gain measurements, real world performance, then you need to be in the far field. So thankfully there are online calculators for this. you plug in your antenna size, which in my case, the log periodic was 30 centimeters from maximum dimension, and the highest frequency of interest was 2.7 gig. If you put those figures into the calculator, it tells you that your antennas need to be 1.62 meters apart. There is another point of reference here, and it's the EMC standards, and you'll find that the standards frequently dictate 3 meters distance between your antennas, and so that's exactly what I used. There was no point me choosing the minimum distance between antennas. I had plenty of space. I wanted to be absolutely sure that I was measuring stuff in the far field. I had enough power that I could transmit. I could detect my signal 3 meters away. That wasn't always the case, by the way, which was why I needed an amplifier once upon a time. But I had enough power to set my antennas 3 meters apart. That's what I did. The next question then of how high now. So this is determined by the Fresnel equations. Once again, there's plenty of calculators online for this, and if you plug in 3 meters gap, if you plug in the lowest frequency this time, not the highest frequency, but the lowest, it tells you that your antennas need to be 0.57 meters above ground, and that's both antennas, by the way. In my case, I set them all to 1 meter. It was just a really convenient way to do things. Once again, there was no point using the minimum distance. As well as that, the pipe that I was buying from Bunnings, the stuff I was building came in 1 meter length, right? So 1 meter was just really convenient for me, and that's what I used. All right, finally then, on the test considerations, I had an earthing cable at times running to the electrical cabinet, and I needed to get that earthing cable back to my test setup, my spectrum analyzer and the battery and that sort of stuff. As well as the earthing cable, I also had my coax cable, of course, and I had a couple of power cables as well, which I was running around. So I was really, really careful to keep all of this cabling well outside of any field of influence. I think the most likely influences would probably have come from noise in the mains cable, just radiating out and possibly interfering. I appreciate. And you might be thinking at this point, well, that's 50 hertz, but no, it isn't 50 hertz. Of course, it's the frequency of whatever equipment I've got connected to the mains. And all of this is really just to keep that noise level down as low as possible. The last thing I want is to choose an electrically quiet site and then go and start generating my own noise and mess everything up. So as well as the cable placement, of course, the equipment placement, absolutely important that's outside of the field of influence. And the way I guess you validate that you've got a good test setup here is through repeatability. So when I was testing, when I was rotating through that 360 degrees, I would take my first measurement at 0 degrees. I would then rotate, taking measurements as I went, and then the final measurement would be at 360 degrees. So what that gave me now was 2 measurements at exactly the same angle, and they should be the same. So to talk about measuring gain or measuring sensitivity then, you've clearly, if you're going to measure a signal in a 3-dimensional space around the antenna, you've got 2 options here. Either you need to rotate, you need to move the test antenna, the receiver around the, let me pause there. Either you need to move the receiver around the transmitter, or you're going to have to move the transmitter around the receiver. You've only got 2 options. The problem with moving the transmitter around was because it's a directional antenna for a start, you can see how I've always, it's not sufficient just to move it around. I've also got to angle the antenna so it's pointing at my test antenna, and that was too hard. So what I ended up with was rotating the receive end, and then also I could pick up my whole antenna and the electrical box and the meter and everything, if I needed to, I could pick up that whole lot and rotate it in different orientations. And by so doing, that allowed me to simulate, or that allowed me to take the measurements in a three-dimensional space. Okay, so just to talk about my transmitting end for a moment, I've already said that my transmitting antenna is basically just it's fixed in so much as it's only going to point in one direction. But I did need to consider moving up and down. And I guess perhaps before I got to this point as well, I thought I might want to go left and right. But so I toyed with the idea of building myself a tripod that could hold my antenna. I suppose I didn't realize it was a tripod initially. But when at some point I started thinking about camera tripods, and the problem with camera tripods, of course, is that they're metal usually, and I didn't want any metal in my test setup because that's going to influence things. And so then I thought, well, I'll make a tripod out of wood, but if you want to make it entirely out of wood, as I did, when it comes to adjusting the height, I wanted to adjust the legs, I possibly wanted to swivel, putting sliders and rotating bits and pieces in it made from wood was just going to be really hard. So in the end, I decided just to keep it all simple, and I ended up with that fixed height, fixed direction antenna. And because I was thinking about uneven ground, maybe I put some adjustable feet on it, but essentially the antenna was built at the correct height of 1 meter. There's a footnote here that I've seen metal antenna tripods used elsewhere, so I don't know. Maybe they just don't have as much effect as I thought. Nonetheless, I needed to keep mine simple, and I ended up with actually a couple of bits of 2x4 and a bit of pipe work. This was my first attempt actually, and it's quite unstable, as I've noted there. You can see in the photo I've got a bottle of water and a rock, because when the wind blew, the whole thing would sort of move around a little bit, and you could see that really clearly on the spectrum analyzer as the spectrum would just dance around. So I firmed this up. Actually, I made this much heavier duty in subsequent attempts. So the receive end. This is the more interesting end. And I had some requirements, so let's just run through what those requirements look like. Firstly, I needed to rotate my antenna through 360 degrees, and as I did that, I also needed to know what angle it was at. I wanted to minimize the metal, as I've mentioned. I wanted it to be easy and cheap to build, and really what that meant for me was I had to buy all my stuff from Bunnings pretty much, because I love just wandering the aisles of Bunnings looking for inspiration. If I've got a project in mind and I don't quite know how I'm going to do it, yeah, I find there's no substitute for walking up and down aisles looking at bits and pieces. So it needed to be easy. It wanted to be quick as well, right? Point number 6 here, it needed to support the cabinet weight. So this is the electrical metering cabinet. And I didn't realize this originally. And it was, I guess, by sheer dumb luck, really, that it was the structure that I built was just big enough and just strong enough to hold an electrical box. And what's not, one of the difficulties with doing this is that the box is frequently off center. So I'll talk about this a bit more, but that was the problem anyway. And yeah, needed to minimize variation. So the whole antenna was built around a Lazy Susan. I'd bought a Lazy Susan bearing, as it happened, some years ago, and it was sitting at home and thinking, I'd like to do something with that one day. And this was the perfect project. It just gave me the rotation, which was the sort of the base part of the whole antenna assembly. And once again, I've strived to keep it simple. So cheap and cheerful. This is what my final antenna looks like. So wood, plastic, glue. The only metal parts in this are the bearing itself and those screw feet as well, which in the end I never used as it happened. You can see that I've marked out degrees. Thing to remember when you're rotating this is that once you've gone all the way around to 360 degrees, you need to rotate it back to the start again. You need to backwards so that you don't twist up the cable. The photo in the right-hand side, top right, is there's a meter there, and you can see how the the coax cable runs right down the center of the tube, and it's done because it was the best way to stop the antenna, the cable position moving, and therefore the best way to get consistent results. If the antenna cable sort of ran down the side of the, if it took a different path, you can see how that path would vary a lot more as I rotated the platform. The other thing just to mention here is perhaps not obvious, is that the distance between the receive and transmit antenna need to be consistent as I rotate. And the only way you can achieve that is that if your antenna is at the center of rotation. Obviously, as I move it further away from that central point, as I rotate 180 degrees, my antenna is now going to be a little bit further away than you see what I'm saying. So I think I've mentioned those 2 points at the top already. When I was using an electrical box as well, obviously not one used in these photos, but when I was, that needed to be earthed, and so I would run the earth cable through the center as well. And very quickly when I did that, I started to see variation in the results as the coax cable and the mains cable became twisted around each other. So I needed a way to achieve a consistent spacing between them. And for that, I used a pool noodle, and a pool noodle I thought worked really well, actually. I gouged out a channel on the opposing sides, and the cables just sat in that, and it kept them all the same distance apart. It was really nice. Overall, the whole thing took me about 2 hours to plan it, to design it, and 2 hours to build it. Actually, $50. I was pleased with that. So I harped on there a bit about why I wanted to use wood and not metal, and I think it's probably just worth just touching on that slightly deeper. I don't want anything in my test that's going to affect the test. I can't allow anything that's going to cause reflections and so on. What that means in practice is that all the materials I use must be transparent to electromagnetic waves, because if they're not transparent, they're diffracting or reflecting or whatever. So it needs to pass through. And the way that this transparency is measured is with a thing called permittivity, which quantifies how transparent your material is. The Greek symbol epsilon is used for that permittivity. And what I ended up with was wood and PVC. I thought it might be interesting also just to show some the permittivity of different materials here. Also, before I mention that, just a quick comment that I talked about relative to permittivity. This table on the left uses the term dielectric constant. They are exactly the same thing. Dielectric constant is no longer a recognized term by, I think it's by the IEC or the ISO standard or something like that these days. So permittivity is used. You can see that, well, metal is not even shown on there because it's infinitely high. Wood also not shown on there, but I dug around, and of course someone's written about this stuff, and I managed to find a paper where a guy had he looks into the permittivity of different types of wood, and he measures them with different moisture contents. He measures them with the grain cut in different orientations, and he measures different. And so you can see, there's a graph there. You can see somewhere between about a permittivity of 2 and 16. So point being, anyway, it's fairly low, certainly low compared to metal. Lower would have been better. Water, of course, is going is going to increase the permittivity. So I made sure, yes, I made sure that it was dry wood. I was using plastic, obviously it is dry. So once again, things that could influence the test. Nearby objects, I've mentioned those already. The other thing just to bear in mind is that in I had a cell phone with me, I had a laptop. I made sure that those devices were set to airplane mode, or ideally just turned off. Careful about equipment and how I ran the cables. Yeah, there was more than one occasion where I did a test and I realised that yeah, that my cell phone wasn't on airplane mode, and I go, oh, you end up repeating the test. So those were the external influences. The internal influences then, these are mismatches in my antenna and cabling. There's all the elements of the spectrum analyzer internally, etc. The losses in the cables and measurement error wherever it creeps into the system, and it will creep in at multiple different points. That said, I don't care about any of these things at all. I can just ignore them because I'm measuring from, I'm doing comparative testing. All these things will be consistent between tests. I don't care about them. Right. Moving on then to the gathering of the results. Yes, when I first started out, I'd wheel my spectrum analyzer out to site, and I would set the markers at various frequencies of interest, and I would read those values off the screen and enter them into Excel. That became tedious quickly, and the other problem with that is that, well, it introduces human error because I'm typing in numbers and I make mistakes. Because of the effort involved, it really encourages me to only use a few test points, so 5 on the screen here. Yeah, so there came a point in my testing where I decided to try and automate that, and the spectrum analyzer allows you to make a remote connection to it. So I wrote some Python code which allowed me to read all of the data points in the blink of an eye, store them all to a file, store them in exactly the right format so that I could just open them in Excel and they were in the right format. And this was a game changer for me, really. It just sped things up immensely and just made the quality of the figures a lot better. And these are the sort of figures that you get. This is what I was looking at. I'd plot, I'd plot my my frequencies over. Sorry, I'd plot my signal strength over the various frequencies, and I could make an eyeball decision just looking at graphs like this, or I would frequently, because they were in Excel, I would run all manner of sort of summing and averaging calculations. Just to try and I suppose consolidate all the data into something that into a single number where I could say 2 is better than 1 kind of thing. Okay. Also, because my results are in Excel, somebody out there in the world has very kindly written an Excel plugin that draws polar plots for me. So I thought this was quite interesting as well. There's probably held marginal interest or marginal usefulness for my testing, but yeah, looks good. Now on to just a few photos then. The photo we're looking at here, I'm testing how the antenna is influenced by the proximity of metal. I don't know if you can see the tape measure there, but I don't know. I was just measuring at different distances from the metal. Photo on the left, you can see, I've rotated my meter. Obviously, I thought in that instance, I thought it was easier to rotate. Oh no, sorry, I realised what I'm looking at here. The meter was screwed hard to the board, and I rotated the entire cabinet, and it's on its side there. And the right-hand photo, you can see the earth lead. So this is interesting. This antenna here was well, it was an antenna that we were using actually once upon a time, and it wasn't great at 700 meg, and I asked the manufacturer to tweak it. They came back with a design, and when I ran my VSWR test, I said that's really high, and so I went back to them and I said, "Can you do anything about that?" So what they sent me was this antenna. And for the eagle-eyed among you, if you look very closely where the just in the left of that antenna where the cable comes in, if you look very closely, you see this. So that is a resistor. It's a 24.9K resistor that's soldered between the two halves of the dipole. And I kind of felt they cheated a little bit when they did this. I suppose my expectation was that they would just improve the antenna overall, but perhaps I didn't word my question correctly. And what they've done is they have actually reduced the VSWR. And I struggled with this for a little bit, but I came to the conclusion that that it was effective at doing what it did, and also that it didn't impact the efficiency of the gain of the antenna. I want to say at all, but certainly didn't affect it significantly. So I sort of found peace with this. Yeah, just you can see my ruler there showing dimensions of those antennas. I think it's worth mentioning, I realized I should have done this earlier, that when I measured sensitivity, what I was actually doing was, well, I was just measuring, recording the power in dBm. Yeah, perhaps I didn't need to say that. So a little bit of history, a little bit of my testing history anyway. This is how it started for me, doing a sensitivity measurement. Level 7 is in an office block where I work. You can see that there's going to be reflections. Obviously, there's a lot of concrete and rebar throughout, a lot of metal in the ceiling and floors, and this certainly would have influenced my tests. I'm using an omnidirectional antenna there, that's a magnetic base mount antenna on a metal plate. Have I got a closer up picture of this? Not easily. So underneath my receive antenna, so that's the one on the big metal plate on the right, underneath I was rotating that through 360 degrees, and I would just print out a circle with degree measurements on it and stick it to that that wooden pallet, and then as I rotated my antenna, I could just see what angle I was at. The whole lot is, as you can see, is lifted up off the ground on some flower pots and wood. So it was a big step up for me when I went from that omnidirectional antenna to a directional. It meant that I didn't need the amplifier any longer. The other thing I think you can just make out in this photo on the left is that I am as far away from all of the walls in the place as I can be. From there, it progressed to some outdoor measurements. So this is an inner city site quite close to the centre of Brisbane. I found a local park. What you can see though is that being urban, there's some cellular activity at band 28, and that's the great big hump on my spectrum. The way I got around this was I just said I'll take measurements in a different part of band 28, and so that's exactly what I did. I've set my markers to avoid that hump, and that way I could make sure I was high enough above the noise floor. You could argue, of course, that as long as my received signal is much higher than the big hump from the cell tower, I could have tested here as well, but I never got to that level of comfort. So yeah, progressed from a printout of circle with some measurements to a proper rotating antenna. I've talked about that. This was another big step up as well, actually. There was a time where I had a petrol generator that I used to power the equipment, and it's big and heavy, and I'd lug it in and out of the car, fill it up with petrol, and it was noisy, and almost certainly put out all manner of nasty EMI, sorry. And so there came a point where I ditched the generator, and I bought myself a car battery and 230-volt inverter. So that was definitely made my life a lot easier. The only downside, I suppose, is I ended up needing 2 batteries if I went out for an entire day. Maybe not much of a downside. Yeah, so there's a monitor in this picture, and I needed that monitor because I frequently couldn't read the display on the spectrum analyzer, just because of the glare from the sun. I was able to get rid of that monitor by when I wrote that Python script, because I simply didn't need to read any numbers anymore. So scripting sped things up, and yeah, recorded everything magically for me. So this is really interesting. I think this is a great graphical representation of how you get reflections off an object. So for this particular test, I was measuring the power at different distances from a metal plate. So and what you can see here is that if you can read the x-axis, which is at the top, that's measured in centimeters, there's a peak or trough about every 6 to 7 centimeters. So just to highlight what I mean there, I would get, if my antenna was, if I look at the 7 centimeter distance, this means that my antenna is 7 centimeters away from the metal plate, and that was a big null in my in the waveform. And then if I moved out to about 10 centimeters, it gets higher, and then back to 14 centimeters, 13 centimeters, I hit another trough. So 6 to 7 centimeters. Now the wave, the frequency that I'm measuring here is 2.17 gigahertz. The wavelength of 2.17 gigahertz is 13.6 centimeters, and half a wavelength is, bingo, 6 to 7 centimeters. I just thought this was a great, just shows you how you get that constructive and deconstructive wave patterns. As I move as I move a quarter of a wavelength from the metal, I go from a fully constructive to a fully deconstructive waveform every quarter wavelength. Just a comment on repeatability. So I've tried to stress that it needs to be repeatable, because otherwise you can't rely on your results. And I saw with my gain results outdoors, and in fact with all of my results, I didn't see a great deal of repeatability, to be honest. Particularly with the gain results, I was seeing 10 dB of variation. Even, I'd rotate the antenna a bit, and then I'd swing it back to the starting position. So I've taken 2 measurements at the same point. And yeah, I'd see 15 dB variation sometimes, certainly 10. And I looked back at some results from a commercial lab, and interestingly, they were getting exactly the same variation. I should just point out that all of the gain tests I did, were also repeated in an anechoic chamber by a commercial lab. So I sent my antennas to a lab, and I said, guys, test them in free space, but also test them in the various meter configurations that I tested. And yeah, they were seeing some variation. At the end, with that, I'd like to thank you for your time.